All right. So converse of the triangle proportionality theorem. We already learned about the triangle proportionality theorem, but now we're going to learn about the converse. Okay, so it's basically it in reverse. And this goes with lesson 12.1, right out of your text. Your essential question. When a line parallel to one side of a triangle intersects the other two sides, how does it divide those sides? Learning goal, I can apply the converse of the triangle proportionality theorem. And so this looks really similar to what I gave you guys for the triangle proportionality theorem, but here it is the converse. So basically it reverses the order. I should probably open up the other one just so we could compare them again because I closed it. But it says a line divides two sides of a triangle. If a line divides two sides of a triangle proportionally, okay, so we have this line cutting through in the picture. And when it does that, we get this ratio where we're comparing this side, AE, this segment of the side, to EB, and that's equal to the ratio of this segment of the side to this segment of the side. So say if we make a proportion from a line cutting it, then we can say the lines are parallel, right? So the triangle proportionality theorem, though, was in reverse. Said basically if you had a parallel line cutting through. Right, so here it is here. If you had a parallel line that was cutting through, then the way it cut it created a proportion. So that's triangle proportionality theorem, whereas this is the converse. Okay, so it's in reverse. So that's what we're going to use today. And there's only 4 slides. This is a quick little lesson. It was just too much to do all in one day. And it's the same section as the other lesson that we did. We're both of these are in 12.1, but just kind of breaking it up here. So we're going to do this slide together. All right. So you do want to have, preferably, you know, side-by-side windows. You would have your Pear Deck tab open, and you would also have our Google Meet open. So that way you can see what's going on as we work this out here. All right. So I'm going to make this guy smaller, just so you can see how many of you are following along. So I have one person who's, you know, started to write on this, which is great. And so we're going to do this together. It says verify that the line segments are parallel. So when we're using the converse, we're going backwards with the triangle proportionality theorem. And right here, it says for this first example, we have segment MN and KL. Okay, and so we can use some tools here like the highlighter tool to go through and highlight things that I want to stand out, like MN. I should probably use the line tool. And MN. Okay, and then we're also talking about KL and KL here. All right, so we want to verify that these two line segments are in fact parallel. And so what we're going to do is consider a ratio of this side of the triangle. Okay, this 42 and 21. That's where this is coming from here, right? We're just taking JM, which is 42, and MK, which is 21, making a ratio, and then simplifying it, and we get 2. And then we're going to take the other side of the ratio, the other side of the triangle. We're going to look at JN, right, which is 30, and NL, which is 15. So here is JN divided by NL, 30 divided by 15, and again, it equals 2. So since JMMK equals JNNL, right, 2 equals 2, so the two proportions, the two ratios in the proportion, they're actually equal. We can then say that segment MN and line segment KL are parallel. That's what these two vertical lines here mean by the converse of the triangle proportionality theorem. And so if you wanted to then add that to your picture, like I showed you in the warm-up, sorry, is like you would put these arrows like this, and that shows that, hey, these two line segments are in fact parallel. All right. All right, so we're going to do this next part together too. I'll use some color coding here just to kind of help us see what we're talking about. We want now to verify that the line segments are parallel. And so I have 10 of you guys writing on your slide. So we do want to continue writing on our slides. You know, it's a really kind of like the way that I've been doing the notes lately, where we're following along and doing stuff together, and you're getting the correct answers because we're doing it together. This would be really great for your notes. So like these are almost like scaffold notes. You can always, you know, do screenshots of this and add this to like a different document. They're available on Pear Deck. You can always go back to Pear Deck and access what you did in Pear Deck, but it only lasts for 30 days. So after that, you don't have access anymore. So you might want to have something more permanent with them. So that's what I mean when we say take notes. It shouldn't take you very long. You can just go back through your Pear Deck and screenshot your work, or you can go through the video and screenshot my work and just, you know, create a digital document of some sort, like Google Slides or a Google Doc. And just put all that information there. All right, so anyhow, now we're going to show that DE and AB are parallel. Okay, and so if I'm looking at the picture over here, here is DE and AB is here. We want to show that these two line segments are in fact parallel, and we can do that with the converse of the triangle proportionality theorem. So if I can create a proportion with the four segments, okay, then I can say that they are in fact two parallel segments. And so they're giving us some information. It says, given that AC is 36 centimeters. Okay, so let's find where AC is. Here's AC. So that would be this entire length, wrong color, let's use red. This entire length here, okay, is 36 centimeters. And so we're going to have to do a little bit of figuring out to get the piece that we need, right? We need to know what this piece is here. And so we know that this piece right here is 20 and this big piece is 36. So with these two numbers here, the Pear Deck code is right here, IRCVYC. And I think I still have it saved to my clipboard. Yeah, so there's the link to it as well, Caesar. You can join our Pear Deck that way. All right, so to get AB, right, so that's this segment. We would take AC, this really long segment, which is 36, and subtract DC, which is 20, and then we get 16. So now we know that this tiny piece here is in fact just 16 centimeters. All right, now the next one I have to figure out is right here. I got to figure out what BE is. But again, they're giving me some information. They're saying, hey, BC is 27 centimeters. So this entire length is in fact 27. All right. And so we're going to fill in here, you know, the steps to figuring out what BE is. BE equals BC minus, what would we subtract? What should go in this box right here? Let's see what you guys are coming up with as you're doing this, if you have the first box filled in. So this person put EC right here, which is correct. Okay, so yes, we do want to write EC there. So I'm going to get my text tool. I'm actually going to just type EC. Okay, and then we're substituting in numbers next, right? So BC minus EC, what two numbers do we want? 27 minus 15, good job. 27, 15. And then when you actually subtract these, that's going to tell us how long BE is. And again, this person has it. See if somebody else figured it out too. And I know if you're doing this on your Chromebook and you don't have a mouse, it's going to take you longer because it's just more things to click and things. But if you have a mouse, it'll be easier to write with the mouse. And so if you are getting really big lines and you don't want big lines, remember you can change the size of whatever it is over here all the way to the left, right? And so 27 minus 15. A lot of us are typing that in now. It's 12. Okay, so I can then type in 12. All right, and I can use the pen tool, pencil tool, whatever it is, to write 12 here. 12 centimeters. Okay, so now that I know all these pieces, these 4 different lengths that I need, now I just plug them in to see, you know, does the ratio of CD to DA equal the ratio of CE to EB? If they're equal, then those 2 lines are parallel. Now, if they're not equal, the 2 lines are not parallel. And so we're just plugging in numbers now. All right, so CD over DA. I'll let you guys kind of work on this one a little bit and see how you're getting it. I have 18 of you responding. So remember, to get your full attendance credit, you do want to be writing in the Pear Deck. You want to have the Pear Deck presentation open and be following along. I go find some students that maybe they look like they're not here yet. Might force open the Pear Deck tab on you if you don't have it open yet. You may have it in a different device if that's the case. Sorry, I can't tell. I can only see what's on your Chromebook. Yeah, see somebody, I just wrote them, I was like, hello, and they're like, sorry, I was unconscious. They fell asleep. 9:38, super early, right? All right. Okay, so what are we coming up with? What's the ratio that's going to go right here? What 2 numbers? This person has 20 over 16. This person has 20 over 16. (20 over 16). 20 over 16. Yes, you are all correct that wrote 20 over 16. So good job. 20, 16. And the more you use Pear Deck, the better you'll get at playing around with the text tools and the drawing tools. Okay, and so now I gotta simplify this. 20 over 16, there is a common factor of 4. So we're gonna divide 4 out of the numerator and the denominator to get improper fraction. What does that turn into? It's not 10 over 7. (5 over 4). This is what it is, 5 over 4. Okay, so what we're basically doing is, I'll try to write this, dividing 4 out of the numerator, dividing 4 out of the denominator, and then that gives us our new improper fraction of 5 over 4. Now, sometimes it's good to turn your improper fraction into a mixed number, but remember, the reason we're doing this is we want to see if these are the same value, and so they may or may not be, but we'll find out. So what are we going to put over here? CE over EB. What numbers go there? CE over EB. This person put 15 over 12. $15 over 12. $15 over 12, $15 over 12, that is correct. We do want to write 15 over 12. And now the question is, does 15 over 12 also simplify to 5 over 4? So we want to divide out our common factor. If I look at 15 and 12, they have a common factor of 3, which I think is the greatest common factor. So if I divide 3 out of the top and the bottom, I'm going to get a new fraction. And does that fraction equal that fraction? What is it going to be? So now this person is going to mix number, which you can do, but then you have to do another step. You have to see, is 5/4 and 1 1/4 the same value? And maybe you recognize that it is the same value, and that would be fine. And this person wrote 5/4, which is what this would simplify to as well. Okay, so 5 divided by 4. Now enter 4. There we go. That works a little bit. So we get 5 over 4. And that is also equal to, because this person was right, it was equal to 1 1/4. Okay, so, you know, if you got the mixed number and then you figured out this was this and this, it's all the same value. So we can see that CDDA, that is this guy right here, is equal to, well, what do we prove it was equal to? We proved it was 5/4, and this was also 5/4, so this would go right here. All right. Using the correct letters, we have CE, EB. And then that means segment DE is parallel to segment AB by what? How do we know these two? Why is it that we could say they're parallel now? It's called the converse of the triangle proportionality theorem. And of course, it's like lots of letters. Okay. So I have it on caps lock, so that's where that came from. You can resize your text so it fits. Theorem's already written here, so you're just going to fill in converse of the triangle proportionality theorem. Okay. All right. So last slide. Look at that. We're on the last slide. And I'm going to put you on student paste so that way I can leave this up if you're still copying this. And what I want you to do is do this last slide. Okay? You're going to verify that TU and RS are parallel. TU, RS, I want you to verify that they're parallel. Okay? So that's basically what we've been doing in this slide over here. And look at that, they gave you all the segment lengths. You don't have to do any calculations to figure it all out. That's very nice. I just noticed that did that. Okay, so you don't have to do any calculations like we had to here. You can kind of just jump into what you see up here for the first one. And so I'm going to give you 5 minutes to do that. And then we will go over the answer. So we should be in our Paradesk tab working on this. I have 10 of you working on it. 14 more of you need to go over your Paradesk. Right. 11 of you working on it. Okay, where are the other 15 of you?
On the water. For me. Just for me, baby. Okay. Oh, there's always gonna be pressure. Okay. Pressure.
Okay, so time is up. We still have 10 minutes left in class, and so let's see what you were able to come up with and look at the correct answer for this. So I got 12 of you to start writing, 14 of you never started. Okay, if you don't participate, that goes into Aries. That's more work for me. I have to like type in little notes and stuff and say that you weren't participating. So participate. Okay. So right here, this first person, they put some color all over the triangle. I like that. And they wrote that VT is to VU. All right. So they wrote a proportion with these two sides. And then they went 12. No, that's RT. RT is to US, so 72 or 54. So we'll see, does that set up work for the proportionality theorem? Maybe. This person just wrote yes. This person put VT to TR, which is 90 over 72. That's how I would set it up. I'm not saying the other way wouldn't work, but we'll see. 90 over 67.5, 72 over 54. We're going to find out. Yeah. So over here, if I do this piece over this piece, that's going to give me one ratio. All right. So 90 over 72. Okay, and then the question is, what does this equal? Does it equal the same as this number over this number? Point 5. Whoa, whoa. Right. So are these equivalent? Is what I'm trying to figure out. And, you know, I do want to kind of look at, see, does it work the other way? Let's find out. Okay, because someone was writing that. They were putting it this way. So let's open up a calculator and just see what happens. So here is my calculator, and let's see, we're going to do 90 divided by 72, 1.25, which is the same as 5/4. Okay. And then over here, let's see, what do we get when we do 67 and 5/10 divided by 54? 1.25. That's 1 1/4 or 5/4 again. So we did get the same answer here. Let's see what happens on the other one though. I'm curious. Because maybe it's another way to do the problem. There are lots of ways to write ratios. All right. So here we're able to show that, you know, those are equal. So let's see what happens here. 72 divided by 90. We got 0.8. So we did this orange piece divided by this yellow piece. Nope, we did this yellow piece divided by this orange piece. And we got 0.8, which is the same as 4/5, right? And so what they changed theirs to here is they still wrote their ratio, but they flipped it. And so they got 0.8. And then for this one, 67.5 divided by 54. Now you're going to have to be consistent. You can't, this is actually going to give us, we already know that's going to give us 5/4. So if we have 4/5 and 5/4, those aren't equating. But if we set them up the same way, so if I choose to write this lower segment, or the segment, I guess, I'm in my mind flipping the triangle. So this, the yellow segment, which is more to the right, if I'm putting that in the numerator, then below the segment that's more to the right, the 54 would also have to go in the numerator. All right, so we have some options there. You just have to be consistent. All right, so I did see someone, they tried to put like 90 over 67. Where is that at? Did you change it? Because I want to see if it works. It might work. Who knows? Okay, I can't find it back, so let's just do it ourselves. I'll clear this all out. 90 over 67.5. What happens if we do that? 90 divided by 67.5 equals 1.333333. So it's 1 1/3. 1 1/3. Now, if I also get 1 1/3, then this is just another way to set up the ratios. So we did the green over the red. What about the blue over the purple? Ah, it works. Look at that. So you found another way you can set up your ratios. There's lots of ways to set up ratios. You just have to be consistently comparing parts that are supposed to be in proportion to each other, if that makes sense. All right, so you can use the way that's in the theorem, okay? You know, just following the rules from the theorem, and that'll always work. Or there's other ways you can do it as well, and it turns out it will work. So we have just proved, and so I'm going to just use the pencil tool here to finish this part, and I'll come down below and do this in white. We're verifying that side TU and side RS, not side, segment TU and segment RS are parallel. All right, so right here we've just proved that VT to TR, okay, VT was green, TR was blue, 90 over 72, that was 5/4. We just showed that, well, it is equal to 5/4 here, which is this red side VU, and that's over 54, which is this purple side US. So since we showed that they are in fact equal, 5/4 equals 5/4, this implies that RS and TU parallel. TU and RS. And to do the parallel, we put the two vertical lines like that. Okay? Since we showed this to be true, because 5/4 is 5/4, that means that those two sides are parallel. And then you can even go in and put those little arrow things, right? I don't think it matters if they're both pointing down or both pointing up, but you do want them pointing the same direction, either both pointing down or both pointing up. Okay, so that went right to the end of our class time today. I thought it would go quicker because it was only 4